Все, я запись включил. Сейчас небольшой проект сказать. Так, где близко. Любая отрицательно определенная модулярная. Ее определите. Четко. Скажем, через это мы будем взять E8 плюс E8 плюс E8 отрицательно определенная.
А четвертое означает, что ты
Где-то.
Что слепой, начинаю здесь издалека.
А нет,
их можно понять.
Вот, в первую очередь,
Самое удивительное, что вот эти группы, написанные с правой стороны, теснейшим образом связаны с решеткой 17.2.26. До другого воина конвер. А он монстр.
все равно чистая.
Потому что если показать
все, что я делаю, не хорошо. Я не расстреляю. Да, но прямая сумма. Слово число нет плохого. Нет.
Если ты перечисляешь. Привет. I would like only to show some relation with the subject which have discussed today. So this is the order of Mathieu group, M24. And Mathieu group is related to the Niemeyer lattice with the following truth system. 24 copies of A1. There is unimodular extension of this lattice. If you take this Niemeyer lattice plus 2 hyperbolic planes, you get a lattice of signature, unimodular lattice of signature 226. It would be one cusp of this homogeneous domain of dimension 26. So this is some possible relation between this stuff and this stuff. So in some sense we continue the first part of our seminar. But this we'll discuss in a little bit. So let's start from moonshine.
Who knows this word? It's in English.
Я спрашивал у Борчерса, но в принципе это как бы считается, ну такая чепуха какая-то там,
Ну,
если.
да, говорят по-русски хорошо переводить как бурда.
Бурда, да, чепуха.
This word has couple of meanings.
Бред.
Ну не, именно бурда, не бред, сейчас объясню почему. One of the meanings is the something that makes no sense. So something that makes no sense. Nonsense. And there's another meaning in Russian it's called самогон. Home distilled alcohol. This appeared during the prohibition, right? And there was a super zakon, the dry law, that people did their own alcohol and they did it during the night under the moon, so it's the moonshine. And this to me, they both come into play when people want to speak about this. And this word that kind of also can be an alcohol or can be a nonsense, right? So basically, it's some kind of part of mathematics now. Math that relates three seemingly unrelated fields. So math that relates at least fields. So one of them is automorphic forms. So another is geometry, algebraic geometry. And topology, and the third one is theory of sporadic simple groups, or something sporadic. Groups. These relations, sometimes that is called triangular relations. This kind of relations is what's usually called moonshine. So all the three fields are very old, right? At least coming from 19th century. So this starts in 1850s. First sporadic simple groups were found by this person, Mathieu. This starts from, at least from Euler.
Yes, maybe early.
Algebraic geometry, for centuries. And usually, what Bogomolov says, right? So if you have some algebraic variety that appears outside of the algebraic geometry, it's always usually very simple variety. Never people in applications can imagine something more complicated than say elliptic curve, A3 surface, some surface, or something very rational. And well, in this field, usually, again, these varieties are not super complicated. These are usually elliptic curves, A3 surfaces, related things, sometimes maybe.
But arithmetically, K3 and the elliptic curves are very complicated objects.
Yeah, the hypercalar. Varieties. Things like this, they can be related. So this whole story, it starts around like the first appearance of the moonshines. I'll give some historical overview. It started in the end of 70s, beginning of the 70s. So maybe first a little bit, couple of words about simple sporadic groups. So in 1850s, Mathieu, he studied the question, like we know that there's finite groups and they have sometimes actions on the finite sets, then they respond to some subgroups. So you can look for transitive actions. And then you can look for, say, two transitive actions. Action of a finite group on a set such that any 2 points can go to any other 2 points. Two transitive. And then you can ask yourself, okay, maybe, and probably everybody who learned algebra last year in my class, they, 2 years ago, know that how to tell two transitive in terms of representation. So, right? Some representation is reduced. But you can look further for 3 transitive, or say n transitive actions. And he found out that if you look for 5 transitive actions, so group acts on the set and such that if you look for all the possible subsets of order 5, so this is transitive. So this is configuration space. 5. Not good. 5. You can map any 5 points to another 5 points. It turns out they are very rare. Anybody knows an example of 5 transitive action or something like something? Symmetric group that acts on n points acts n transitively, right? You can map any n points to any other n points. Already, alternative group doesn't act n transitively, it acts n minus 2 transitively. Yeah. But it turns out it's very hard. And if you look for 5 transitive actions, then apart from that, there are just only a few of them. And he constructed some 5 transitive actions on 24 and on 12 points. On 12 and 24 points. The constructions, these are related to some very strange thing. Like if you look for symmetric group Sn, and you look for automorphisms of your group, then you always have inner automorphisms, and sometimes there are exceptional automorphisms. Maybe people learn for symmetric group S6, it has an outer automorphism. S6 is Z mod 2. And this is something unusual, something exceptional, usually. Right? For other n, it doesn't exist. And using this automorphism, you can construct some bigger group that acts in 12 elements, basically taking 2 copies of S6. And it again has, this will be group M12. M12 is kind of doubling of S6. And this M12 again has some automorphisms, outer. Again, Z mod 2. You can again double it again to get the new group, M24. And this is kind of doubling of M12. In this M24 itself, it doesn't have any outer automorphisms. So out M24 equals M24 itself. On the inner automorphisms, it's a simple finite group, some subgroup of S24. I wrote here its order. It's ordered. If you have internet, you can Google for this atlas of finite group representations. And if you find this web page, then you can look for most of the groups you like. For example, this and more, or you can use any algebra system, graph, mountain, whatever. So, in middle 19th century, this person, Mathieu, he constructed this group, And also you can look for stabilizers of 1, 2, or 3 points, and it turns out that when you have enough of those points, those stabilizers, then they already are transitive on 11, 10 points, or 23, 22. They still simple. So there are basically he constructed five sporadic groups, which are now called material groups. So M24, M23, M22, M12, and M11. You can look for some stabilizers of, say, of this guy. It will be a group acting on 21 point, and it will tolerate some known. They come in there.
Maybe one remark,
Yeah.
because we're in algebraic geometry laboratory. This material group are crucial if you would like to study a finite automatism group of case-free surfaces or in Rickrey surfaces.
Yeah, so there's a flow of Mackay here. But in the middle of 19th century, of course, Kummer invented Kummer surfaces, and the things existed, right, in the Platonic world, but did not know about each other yet. I mean, at least people didn't know that they know something about each other. So that's one of the very first sporadic groups. And then the story with sporadic groups, it has a gap of 100 years. Right? So for 100 years there was nothing happening there. It was very calm and quiet. And 100 years later,
Finite group revolution.
yeah, there was some big progress, revolution that started from the Fate-Thompson's theorem. Theorem that says if you have a group of odd order, then it's resolution resolved. Группа нечетного порядка разрешена. Solvable. Yeah, so groups of odd order are solvable. So if you have a simple group, it should have even order, and it has interesting two-syllable group. And you can use this two-syllable group to kind of specify them, exploit the structure. So Fate-Thompson theorem, and after that, they started to make the new sporadic groups as the hot pies. Just many people, like there was a guy called Jalkин, who made 4 groups. Maybe one of the first new and one of the last new groups, and many others. And it turned out that, except for some finite simple groups that come in the classes, like alternative groups, PGAN, PSO, PSP, and some other Chevalier groups of exceptional type. The rest, they just they found like 26 of them, 24 sporadic groups, finitely many. And the kind of theorem was theorem. Classification of finite simple groups says that there are, except for Спросить можно, а писать местно. 26 or sporadic groups.
You see again, 26. Why
Yeah,
is the
26. So 24. I don't remember how many. Also, there are discussions, maybe some of the classical give such.
Do you have the proof of this theory, this theorem? We believe that this is true, but yes, but do you know any mathematician who read, not wrote, but who read the proof?
Yeah, so the proof of the thing, it contains tens of thousands of pages. So the first start for this Fate-Thompson theorem, the paper was so big that it took either 1 or 2 journals of Pacific Journal of Mathematics, whole issues. Like the whole issue contained only this paper, so it was published like that. And actually what I heard today from Voevodsky, that this theorem now, it's verified. So there's a person who has a team, like they verified, they have verification system code, and they programmed the huge library, and so this particular thing already completely verified.
By computer or?
By computer, yes. So there's a verification system code, and also like what we also spoke today, just And basically, it's a proof of concept. If you really like to have it, you can even verify this. So far, it's something unknown that maybe no living being so far sure about this all. Like there was Daniel Gorenstein who knew at least the strategy and how to reproduce it, but now he is dead. There are some ways how to reprove it now. I saw there's some notion of the fusion category. Right, instead of looking for sets, you can look for some categories, and some people are now trying to redo this thing in a more general context. They embed groups and they slightly more general thing, so-called fusion category, and then try to classify these fusion categories. Supposedly, in some years, maybe they'll have the new proof, maybe some more sporadic fusion categories.
Maybe new group?
Maybe new group. This happens. That's often happens. 100 years later, you get something new. And the 26 sporadic groups, they come into 4 lines, so to say. There's a happy family. So there's a happy family, and there are pairs. So 6 pairs. So pairs means that those that are cast out, thrown out, right? So those not invited to the family. And happy family, every family has some generations, so it lives on 3 generations. 3 generations. And in each generation, there's a patriarch. So one patriarch is Mathieu M24. Actually, these are the 3 patriarchs of the 3 generations. So the first generation is Mathieu generation. There are basically 5 Mathieu groups there. Second one is Conway generation. And the third is so-called monster of Gris Fisher. Originally, Gris, he wrote a paper that called the friendly giant. Friendly giant. But that's not, the name didn't was as popular as monster. So this monster is the biggest of all known sporadic, of course, groups. Right? So what does it mean generation? Everybody in generation is some sub-quotient of this. Maybe you take some group, then some quotient. Because subgroup might be not similar. So there are 3 patriarchs that are out here. One is Mathieu, another Conway. John Conway had 3 groups, that the bigger one. And the third is this monster. And there are some more or less nice understanding of these 2 groups. As we discussed, we can relate them to something that we might like, to some coding theory, to some geometry, to something.
Yes,
something physical and something small.
I'm sorry. Yeah. M24 is simply the automorphism group of the famous Galilei code.
Yeah. So there was this code used for sending signals to the moon.
Yes, it's very practical.
And M24 again, it just acts on the set of 24 points. It's not a big set, you can write it. And there are not so many elements. You can write them all if you want.
And Conway group is a group of automorphism.
Conway group is a group of automorphism of each lattice. So
lambda 24.
Yeah, so this is related to so-called each lattice. Lambda. So it's basically automorphisms of lambda model plus minus 1. You have always this automorphism plus minus 1. It's central. So automorphisms of lattice cannot be a simple group. But it turned out that they're almost simple after this. So this is just 24-dimensional lattice, positive definite, without any roots. There's no elements of, no vectors of length 2. It's a mini classes, and its automorphic group is this Conway group. It took him 1 weekend to make something to figure out abstraction. And so this one has 24-dimensional representation, if you like, and this one doesn't have any good representation, right? So the smallest representation, reducible representation that it has this dimension 1000, this one, right? It's huge. Also, if you look for the smallest subgroup of this guy, it's related to so-called baby monster, the next group. And if you want to act on some finite set, the set will be huge. You cannot make many feasible ways. If you want to write them as matrices, these matrices will have this size. Yeah? 200,000 times 200,000. You can say it's a group generated by 2 matrices of this particular size, but it's not quite useful keyword. Also, it has 194 irreducible representations. Yes. So actually, originally, what people found out, they didn't yet know that the group exists, but they wrote a character table. Some matrix of much smaller size, 194 times 194, and then they actually made some constructions to prove that it exists. Even till nowadays, there's no really good understanding of what it acts on. Like the groups are often the some symmetries of something, and there are no nice answer like symmetries of what is this monster.
Until now.
Even until now, I mean, you can look for the very nice 3-page maybe review of Borchers that was erased from here that says what is a monster, and then he says he gives maybe 4 of the answers that we have, and he didn't find them satisfied. And so what is the moonshine? So at some point where people discovered that there might exist this very, very big group and had its character table and already might know what its order and so on, the Thompson on seminar Bourbaki, he made a talk. And basically Thompson was presenting like what should probably saying that probably there's a new group, and he put it so that here I put like it's often useful to write it, decompose it into primes, right? It's a very big number. The number itself is more than protons and Jupiters. People who work with this monster, it's one of their key trademarks. So more than protons and Jupiter, but I can write it in this form, and you see there are how many primes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I thought it's 15, maybe I missed one. Maybe one is missing. Okay, you can check it later. And on the seminar for Bakin, there was Andrew Ock, this mathematician that I wrote here, and he told that absolutely independently, he proved a theorem about automorphic forms. Right, so that's for those who Ock's theorem. Ock's said the following. So you have the standard group like a cell to Z. Right? Inside the cell to Z, there's just matrices A, B, C, D, A, D minus B, C equals 1. And here we have the subgroup gamma 0 of, say, P. Yeah, that's C equals to 0 mod P. That's a congruent subgroup here. And we can consider the modular curve. You can take H, modular gamma 0 of P, that's a modular curve that is studied. But you can do something more. Like this group is, if you put it inside SA2R, then this group has normalizer. You can consider the free key involution. Z goes to minus 1 over PZ, or if you like to write it as matrix, like this matrix. And this free key involution, it's a normalizer of this group, so you can consider the bigger group. So here, gamma 0 of P plus P, so to say. It's just the group generated by this group and this involution. Twice bigger. So our group is subgroup of index 2 inside this. And let's take quotient by this group. That's the notation that they use, very, very useful notation. You start from this group and then you add one involution. And this is a curve, right? And you can ask yourself, what's the genus of this curve? And the theorem of Ock says that the genus of this curve equals to 0 if and only if P is prime. If P belongs to finite list 2, 3, 5, 7, 11, 13, 17, 19, 23, 31, 37, 47, 59, and 71. I'm missing one. There should be 59. Ah, 29.
29.
Yeah, 29. I remember there was some discrepancy with this 29 with some of your talks, but it doesn't appear to me. Yeah, so, and Ock proved this theorem maybe 1 year, just a few days before the talk of the Thomson, and he said the same list of primes. Okay, it's fine.
Please add 29.
Yeah. 29 was given by Jack Daniels. 29.
In the list of primes, in the list of primes, not 37, but
There's no 37, right? But something close. 41, yeah. And here, yeah. Thank you. 37 does not matter. 37 divides one of the parias, but not the monster. So, and then the Ock thought, okay, you know, it's very strange because just independently in two different fields, field of orthomorphic forms and field of simple groups, people got two sets of primes and the sets coincide. Set of 15 primes. And he thought, okay, I give battle of Jack Daniels to anybody who can explain why these two sets coincide. Why primes that devise monster are the same as the primes that this curve is genus 0. Or you can say that there are no automorphic forms for this group. Right? I mean, the same basically says. And you still have some chances. This battle was not reclaimed. So that's formally it's an open problem, but there was some progress on solving this problem. And it was maybe the first part of the mystery, but not the last one. Very soon, John Mackay's correspondence, probably you know something else. He made even more strange thing that this classification, this very, very big groups, he related to something that ancient Greeks would appreciate, to icosahedron, cube, to Platonic solids. Basically, well, there's a long connection from Platonic solids to exceptional Lie groups and to simple sporadic groups. And, so he was first doing probably group theory, and then he switched to automorphic forms, and then he noticed one very strange coincidence, right? We started this function. That's not a modular form, it's a modular function, right? It's meromorphic, it's full of order 1, you see it, and we can take its expansion. So this number 744, by the way, everybody might like it, 744 is 3 times 248.
Yeah, so here we can change it constantly.
Yeah, he noticed that 248 is dimension of E8, but this constant is arbitrary. You can choose it. You can just erase it if you like. But the next one you cannot. Next one is fixed. It's half model, right? You have a curve of genus 0. You chosen a cusp, so you look for decomposition that starts from 1 plus Q, kill the constant, and this is a region. And he looked for this number, and then he see that this number is 1 plus this number. And this number, as we just discussed, is the dimension of the smallest representation of this group monster. Again, connection, or maybe some not connection. So somebody probably after this thought maybe he's speaking moonshine. And that's the origin of the name, right? So home distilled alcohol, sometimes why this is called moonshine, because of this Jack Daniels, of the proposed bottle of alcohol. Another about because it seems very unlikely that there's any connection. You know, there's a law of small numbers. If you have two small numbers, you can relate them in any way. But when it comes in a big quantities, and then it came in big quantities, you cannot do it. And then Thomson, he looked further for, also Mackay looked for the next number. And if you look for the next number, you can also write it down as sum of representations of sum of dimensions of reducible representations of this group with very small coefficients, 1 or 2, like you have this representation and the next one. The next one is already that big, something like it's wedge square. Thomson, he continued that, okay, so here are dimensions, but also, and for the first terms, there's a unique way how you can write it down using only small positive numbers. But then if you have some representations, then you can do other things. You can look for its character, right? You can take any element, G, and consider the trace in our ends.
I can tell you one more fact which is not known. It's known only for me and Mackay. Then for this prime, this is exactly the list of prime for which the space of the Jacobi cusp form of weight 2 and the corresponding prime index is 3. You consider Jacobi cusp form of weight 2 and this index is exactly the list of all prime indexes for which
maybe
the
except
space
for
is
29 or something like that.
It's true.
So then you can consider G inside group. So these representations. G inside G of some trace Tg of Q. Some trace of Vm G times Vm. Yeah, so this is about Mackay-Thompson series. And then maybe starting from the very beginning, you can first construct your representations, then construct this power series, and then you get not one, but 194 power series. And then what Tanday and Norton figured out after this guide, all these power series, they are modular, Haupt moduli for some curves of genus 0. So there's a correspondence between conjugacy classes on index elements of G, conjugacy classes of monster, and some subgroups of Haupt moduli, Haupt moduli for some particular subgroups. This is a paper of Conway Norton that's called Monstrous moonshine.
Question.
Yeah.
This generating function of characters, right? This Mackay-Thompson series.
It's just a function.
Here, generating function because fixed power, if you fix particular character of.
You can take them together and take characters.
So this is the generating function, it's called. And is it the modular form or what?
Yeah, so for each particular G, it's a modular form for some particular subgroup. Not modular form, modular function. Haupt model.
Modular function.
So you have some subgroup of
Weight 0.
Weight 0, okay.
You have some subgroup between gamma 0 of n and its normalizer. They have the full description of those subgroups. And this subgroup has genus 0, the quotient has genus 0, and then you look for some particular cusp and some particular expansion.
Do you know any interpretation of this function as the index in the theory of like AT index?
I think it's called Hirzebruch price problem that's open to find some topological manifold with action of those groups. And then if you found it with some conditions, then automatically written genus.
Genus would be this series. This is really genus, right? In the series.
It's an open, another
No,
open.
conjecture, whatever. It's supposed to be a related genus.
It might be.
Okay.
It might be, but
What variety?
Well, we
Nobody knows what
nothing
is
is about
variety.
variety, but it's supposed to be some kind of genus. Okay.
It could be. One of the approaches that did not work. So there's this correspondence, and still, like, they wrote that this correspondence, but it was still impossible to prove it. Like, we know it up to good precision. So then later this particular representation of the monster was constructed. So people already had the representation, and still there was a question: is it true that if I consider for this representation its character, then it's a modular function? Right? And it took maybe 10 years to Borchers to prove it, and then he proved that indeed these are the modular functions, these are the Haupt moduli, and he used some generalization of theorem for Kac-Moody Lie algebras and introduced some understanding of what is conformal field theory mathematically, so-called vertex operator algebra. And one of the answers that he gave then what is a monster, that okay, so monster is automorphism of monster vertex operator algebra. He constructed some vertex operator algebra, and that is automorphism. Like, in maybe some kind of down-to-earth terms, what physicists told that you have to consider, you have the Leech lattice, you can embed it into real space, 24-dimensional space, take the quotient of the space by the lattice, right? You have the metric. It's a 24-dimensional real torus, and then you look for kind of sigma model for some physics, conformal field theory happening on this torus, but that's not all of the truth. There are something called orbifoldization that I cannot explain. You look for orbifoldize, make theory on these things, and then you get some. Borges made some mathematical extract from this and was able to prove it, and that's one of the most classical stories of the moonshine. But that's not.
Why this doesn't give an answer to the question that this is a group acting on something like.
No, it's not variety.
It's not a variety. It acts on the conformal field theory. That's.
Well, you just said about the vertex algebra, saying that it's acts on.
Originally, how monster was constructed, right? So it has this representation. It has this representation, and then when it has this representation, people start to look what are the invariant forms of these representations, and then they found some Gris form. If you have character table, you can see how many of them. And then he found something, some kind of tensor that he called the Gris algebra. It's some commutative but not associative algebra. If you like, okay, monster is the automorphism of this commutative non-associative algebra. That's its original construction. But this algebra, they are not natural, right? Why this algebra appears in nature?
So it's algebra of some differential operator.
Yeah.
Yes, that's acting on operators.
And then it turns out like in this vertex operator algebra, it's one of the first pieces of data. Okay, so this Gris algebra is one of the first pieces of data of this vertex operator algebra and around. And well, okay, vertex operator algebra, they seem more natural, right? Because they something that responds to make conformal field theory.
But this is not a operator algebra because it's only generators and relations.
Yeah. But it's natural for some people, and for some, like, it's not algebra geometry, still, not enough algebra geometry. And there should be more topology, algebraic geometry behind. And that's one of the reasons why he did not reclaim this bottle. He proved only one thing, that why these functions are modular. Why starting from this model, you get modular functions. But also, the question is both ways. There's an explicit description of what modular functions you get. Right? You can solve the problem in automorphic forms theory, and then you get these functions. And then it turns out that these functions are traces of some representation that related to monster. He told how starting from monster, you build the representation, and then you get an automorphic functions, but other way around, starting from automorphic forms, why you come to the monster, it's unclear. And it might be something else behind. That's why it's battle might still be raising. So, and this is something related essentially, okay, to elliptic curves, maybe, right? So, this thing, so it was automorphic forms, with moduli of elliptic curves for some reason. Okay, moduli of elliptic curves related to some sporadic groups. But there are more of the moonshine things. Some of them are much simpler. Probably now I'll tell about some geometric moonshines. This is a little bit less geometric, but it contains. So there was some arithmetic of moduli of elliptic curves and some moonshine responds to the monster. There are some other things that people sometimes notice, like 744 is 3 times 248, right? And there are even simpler things like 24, the favorite number of many people. Let's say 24. If you work with modular forms, you have lots of those 24s, you can relate them to a set to 0 to something else. One of the descriptions of 24, who knows how to describe number 24? Some canonical description. What is canonical definition of 24?
I can give one. This is
yeah, you know, but my
yes. No, maybe it's my description is not standard. Let's consider the multiplicative group.
Yeah, this is the standard. Yeah.
Modulo n.
Yeah, that's right.
And this is the maximal n such that all multiplicative residues are square root of 1.
So 24 is maximal length such that Z and multiplicative group is proportional. That's one of the things how to.
All elements are square root 1.
But okay, so that's for group theories. But what is 24 for geometers? There are some geometers. Rodion, what is 24 for you?
24 is
Euler number of K3 circles, of course.
Maybe also because of the modular stack of elliptic curves. Because
That's for Artem. Yeah, so elliptic curves is something here. Maybe this understanding of 24 will give better understanding of this.
Because for SL2Z, if you take the double cover of SL2Z, then the commutator has index 24.
Yeah.
It's exactly proof of.
also 24 is minus 2 over minus 1/12.
Yeah, that's also. That's Z of 2, right? Z of minus 1, right? 2 times Z of minus 1. Minus.
This is minus 2 over.
Right. Minus 2 divided by Z of minus 1. For this, it's related to their dimension, right? Because there are 26-dimensional space, and when you do this light quantization, you subtract 2, otherwise you have problems among this. And okay, so what I said that there is another kind of moonshine that relates some geometry of K3 surface. Okay, K3 surface is 24, and 24 is
The number of
24.
Leach lattices, or the number of Niemeyer lattices.
Right, so there's Mathieu or maybe sometimes Pondé. And there are various kind of moonshines that relate now again. Geometry, K3 surface, and sporadic groups, either Mathieu group, and 24, and 23, or Pondé group. One of those things I'll give as an exercise now, okay? Because it's unpublished, so then you can do the exercise. Prove something that's not in the literature. So K3 surface is irreducible holomorphic symplectic manifold, hyperkähler manifold. And there's a procedure how you can construct more manifolds like that called Hilbert scheme. So Hilbert scheme. So I have S, and to S I can associate S and I consider all ideal shifts such that the quotient is n-dimensional. Starting from one surface, I get lots of manifolds, a whole series of manifolds, right? Now I can write down something like generating function sum n at least 0, Euler number of S to the n. And what you get? By the way, on this Monday, to Moscow comes Manfred Leonard. Manfred.
You have to add maybe q to the power n or something like this.
So he will read for lectures.
Добавить производящую функцию.
Да. Да. Let's put q to the n. And this formula was probably discovered by him first.
I'm not sure.
I'm not sure, but he was one of the
Goethe, I think.
Goethe is later.
Later.
Leon Verbitsky, Goethe, okay. Let's put here some nice names. Verbitsky, Goethe.
I read this as in Goethe.
But this is the beginning of 19th century. So what does it equal to? Who can tell? What's the generating function for the Euler numbers of Hilbert schemes of points on the K3 surface?
It should be modular form. And very remarkable in this one.
But actually, it is not modular form. It depends on how you write the generating function. So, any ideas? Okay, one of the ways how you can prove it. So, you can consider derived category of this Hilbert scheme. And that's a thing called derived Mackay correspondence. That's the same John Mackay, by the way, right? Derived high correspondence. Let's say that it's equivalent to the SN equivalent Hilbert scheme of the Cartesian power, essentially. Basically, what does it mean? That you have your geometry and you take a rest product of your geometrical variety, commutative and non-commutative varieties of a stack point modulus. And after this product, it's essentially something kind of like symmetric power of the right point. So what does it all say? What I would like to say, that homology, essentially homology of a Hilbert scheme, and that's already theorem. Okay, T surface may be still of Manfred. But essentially that okay, maybe let me give you an answer. I won't give you a proof, I'll just give you an answer, but in the last week maybe prove it.
Yes, but today we have on the introduction.
Yeah, and so one product of 1 minus q to the m minus 1 minus e of s.
Delta function.
So this is partition function, right? It's sum p of
if we add one term, then
n
we get
q to
delta
the m.
to the power minus
Yep,
1.
p of n is the number of partitions.
To the power minus
P of n, number of partitions. And here I just take this function and then take it to the power e of s, where e of s was Euler number of my original surface. Actually, this doesn't depend really on your surface. You can put any surface if you like. But since we know that K3 is related to 24, then we substitute it for K3, right? So sum E of K3m q to the n, it equals q to the minus 1 times delta function. Right? Because this is almost the modular form up to q to the 1 power.
To the power minus 1.
To the power minus 1.
No. Then q to the power. Then q to the power.
Yeah. So q divided by delta. Q divided by delta of q. There's also yellow aspect.
This is again Borch's product.
Yeah, but this is again Borch's product. But this is not yet an exercise, right? So I wanted to do an exercise. I want to twist this thing. So we got one modular form. Let's construct some other modular forms. This way we related two things now. K3 surfaces, right? Geometry and modular forms. But we want sporadic groups. Seems not to appear here, but it should appear, right? So how to introduce the sporadic groups? Let's look for situation when I have some group G that acts on a surface S. Right? And the construction of a Hilbert scheme, it's functorial. If my group acts on some variety, it acts on its Hilbert scheme. Right? And then all homology, they become representations of this group. Right? Any kind of homology implies that G acts on the Sn for any m, and then G acts on homology of Sn, say this coefficients complex. So this becomes just representations. So before I computed the Euler number, just dimension of this representation, but now I can take trace for any element G inside G. I can consider the sum and at least 0 trace of G on the space, on homology Sn C. Or maybe you need to take super trace, but for K3 and you have only even homology, so just consider the trace. Okay, now you can ask yourself a question. So I'm given a K3 surface and I'm given some group acting on it. Maybe for this trace I need just only cyclic group, right? Somehow to motion. What I will get, what functions I will get. Right? So that's an exercise. Let me write it down. So maybe let me put a theorem of Verbitsky, Gödge, and others. Okay, let's put Gödge. Gödge, then, and others. Homology of Hilbert scheme of endpoints is isomorphic to symmetric powers and symmetric power of homology. Okay, let me replace S with X, so we'll see what is symmetric power and where is the surface. X. X. Yeah, so you have this isomorphism, right? So if you know just representation, this representation, you know all the other representations. So everything you want to know, really. So question number 1. It is closed by Nikulin. Let's pick here to this. So I have G acts on. So what are finite order automorphisms of K3? So this question is closed, and now open question. So given X K3 surface and G acting on X, finite order automorphism, find this sum and is 0 trace of G on homology of X and times Q to the n. So the answer will be some particular modular force again up to this Q to something. So let me give you first the answer of Nikulin. So this problem was closed by Nikulin, but understood well maybe a little bit later by Mukai. So if I have a K3 surface, then sometimes people don't like just 24, they break this 24 into pieces. 1, 21, 1, 1, 0, 0, 0, 0, right? You can write Hodge diagram. And we see here there's a one-dimensional space, right? Global sections. So omega x is trivial bundle of x, so global sections of x omega x is global sections of x of x. And it's just one-dimensional space, C times omega. Omega is holomorphic two-form. There exists a unique holomorphic two-form. And then we can ask ourselves, if I have a group, if I have any group acting on my variety, it automatically acts on all those spaces. Every space becomes a representation. So here I have a character. Right? So by definition, Nikulin says that action is algebraic, action is algebraic. Or sometimes people say now pleomorphic symplectic. Pleomorphic symplectic or just symplectic. If for any G star of omega equals to omega. In other words, if this representation is trivial, if this character is trivial. Right, so now theorem of Nikulin. Theorem of Nikulin. If G to the n equals to 1, so some finite order automorphism, and G acts on X and algebraic, G star of omega equals to omega, then n is bounded by 8. N is bounded by 8. So I cannot have it too high order. It's a little bit different from elliptic curves, right? Where you can shift by torsion. I mean, it's any kind of torsion. Here it's not possible. Контекст времени.
Почти полбеда было, так что мы как-то-
Okay, so then maybe I'll first finish with one of these moonshines, then give only some sketches of the others. I'll tell in more details later. I'll give you a map
But
of
today we
moonshines.
have put in introduction.
Yeah, today in introduction, so I will just draw the sketch of moonshines and some of their relations. But this one is, since it's an exercise and not published anywhere, so you can, this exercise you can do. So, what Mukai noticed?
Сергей, может быть, на этом ты сегодня остановимся, чтобы остальное не помнить, потому что там я по именам-то вижу, там...
Я остальное просто скажу какие-то слова.
Да, ну там требуется...
Я не буду.
Не помню.
So, Mukai, he found this relation with K3 and Mathieu. And so, K3, maybe that's the first relation, that K3 group that is related to K3 surface geometry related to sporadic group. Basically, it was not first noted by Nikulin himself. So he told the following thing, that if you look for... Что? Никулина? Что если у вас есть симплектрический автоморфизм, порядок ограничен V7. Да,
Да,
ну,
симплектрический.
он называл их алгебраическими свои статьи.
Сейчас
Сейчас называется
симплектрический.
симплектрическими. Потому что сохраняется гламуром симплектрического кода. So, what Mukai noticed that if you look for the trace of G on homology of your X, then it depends only on order of G. And actually the representation itself depends on the order of G. You can write down what is the representation, what are the eigenvalues, right? The eigenvalues are some roots of unity. That's related to the fixed points, of course. Mukai's original proof was used of the holomorphic of values, fixed point formula, holomorphic and non-holomorphic. And then he wrote a table of those things, and it turns out, and moreover, these traces are coincide with values of a standard character of M22. What does it mean? So you have these numbers 1, 2, 3, 4, 5, 6, 8. And trace of the 1, 2, 3, 4, 5, 6, 8. And then you get here numbers. Here's 24, the dimension 8, 6, 4, 4. Actually, I can tell what is the number. This trace of G equals to 24 divided by psi of n. Where psi of n is the function that I like, the difference function. It's n times product p divides n 1 plus 1 over p. Or in other words, it's the order of SA to Z gamma 0 of n. Index of this group, of the modular group, that's a particular number. So for n equals to 1, you put psi of n equals to 1. That's the convention here. For example, psi of 2 is 3, right? Psi of 3 is 4, psi of 4 is 6, psi of 5 is 6, psi of 6 is 12, so we need to divide, and we get 2. And psi of 8 is also 12, so we again get 2. And these traces are those numbers. And or maybe it's not traces, maybe it's number of fixed points. I might be a little bit wrong. That's either traces or number of fixed points. You can relate one to another. Anyway, so and then it turns out maybe those traces or the others are you just have Mathieu group M24. It was embedded inside S24, and it has the standard representation just on homology of these 24 spaces, functions on these 24 points, it's 24-dimensional space, you have representation. Inside M24, you take a subgroup M23, the stabilizer of one point, and then you look for its conjugacy classes, and it has not that many conjugacy classes. It has one conjugacy class of order 2, one conjugacy class of order 3, one conjugacy class of order 4, of order 5, of order 6, and even of order 8. And the values of this character, this particular character, 24-dimensional representation, it's reducible from 23. It has two-dimensional space of invariance. It's exactly this number. And essentially what the theorem of Mukai says. Theorem of Mukai says that if you have a finite group that acts on a K3 surface by symplectic automorphisms, so finite group G can act symplectically on K3 if and only if two conditions are satisfied. First condition, G can be embedded into a subgroup M, into M23. And second condition, dimension of this C24 G invariance should be at least 5. That's theorem of 1992, I think. First condition is absolutely exciting, right? It relates geometry of K3 surface to some sporadic group. And second condition is a little bit disappointing, right? So, for example, Mathieu group M23, it has element of order 11 or element of order 23, but it cannot act because then this invariance cannot be 5-dimensional, they're less. And it's obvious that they cannot act. So it looks like a tip of an iceberg, right? This theorem says us that geometry related to some interesting sporadic group, but some constraints, some non-ideality of our geometric world prevents us from seeing the whole picture, right? So maybe the notion of the action, notion of geometry is too weak, right? So we might go further. So people try to understand better how it can go, and there are various approaches. So if you look in the paper of Mukai or paper of Nikulin, also this theorem was reproved twice by Xiao and by Kondo. For example, proof of Kondo, it uses only lattice theory. Mukai's proof has some nice geometry plus absolutely killing group theory. You need to study the Silas 2 groups, and it's very hardcore. And the Kondo's proof is very simple. It uses only lattice theory, and Xiao's proof is even more geometric, closer to some Nikulin's approaches. You need to look for the quotient of your surface by this group, then resolve it, then you get again K3 surface, write some Kulin's formula and so on. And still, so if you look at this, then you know the traces, right? If you know the traces, you know what are the eigenvalues, you can solve my exercise that I gave to you, right? Take a K3 surface, take some element like that, and then look for what will be. Find the representation, you have some particular representation, you can just take it in the atlas, right? So go to the atlas of finite group representations, take Mathieu group M23, and it gives you all the information you know. Then compute symmetric powers, and for symmetric powers there's some, any group theorists know how to do it, right? It's useful to take logarithm of the things, then you just need to apply Adams operations, and Adams operations is very easy. We replace G with G to the K, and then you replace them. So hopefully till the next time you can solve this exercise, and then you get some modular forms again. And again, you'll get exactly those modular forms related to Mathieu group. And okay, later I'll tell some more stories about people independently relating Mathieu group and Mathieu group and automorphic forms. There's works of Mason that I didn't put here. And there are more relations of K3 surfaces and again, sporadic groups and automorphic forms. One of this is Yao-Zaslav's formula. You look for rational curves in K3 surfaces, and then you try to count them. And the generating function for them will be a modular form. And there's another work of Lian and Yao. You look for mirror of a K3 surface, or maybe you count them in some other way, the rational curves in K3 surfaces, or better, not K3 surfaces, but finite triplets. And then again, the generating function will be expansion of a modular form in terms of a Haupt module, something like that. And some are very recent. It's 2010 and started from 3 people from Japan, 2 of them working in IPMU, Hiroshi Oguri and Yuji Tachikawa, and also a person from Kyoto, of Noguchi. And their thing again relates. So the thing about Mukai is, see, it looks like it's cut out. You see, you have instead of M24, you have M23 and not whole M23. So these 3 people, they found some relation to M24, like if you look for elliptic genus of K3, elliptic genus of K3, And then they look for its expansion, and then again they see the dimensions of M24 now, not M23, so M24. And then it made a big hype, like it 5 years ago, and now lots of men and women, they writing millions of papers every year, like, because it's when it's related to theoretical physics, it expands exponentially. So they're writing more and more and more, and there are some understanding, but no good understanding. So not something like that. Satisfactory.
It's more or less reduced now to Borch's scheme of the proof.
Yeah. For example, this theorem was resolved in terms of, say, of sigma model by physicists. I myself had the idea that you can resolve it in terms of the direct categories, and indeed for direct categories you can replace 5 with 4, and there's a lot of hybrids that essentially shows hybrids. But still not satisfactory. Okay, maybe instead of 5 you have here 4, maybe instead of M23 you have M24, or even a Conway group, it's more complicated. But those restrictions seem kind of arbitrary to go out of this. And there are so many of various subjects, and like there are lots of the things that geometry, K3, some sporadic groups, and automorphic forms. And still people even don't know much like how it is related to this monstrous moonshine. There might be some way for monstrous things from there. Even from there might be more. Since it's an introductory talk, I just finish by now, solve the exercise and to them.
I'm sure that here we have not only exercise, but very good subject for,
let's
say, for diploma, for PhD, for habilitation, and so on, for fields, Netherlands.
Yeah, maybe you can get this.
Question about this elliptic genus, this phi 12 that Valero was talking about.
Yeah, I can't forget to tell it. Actually, because maybe of our illiteracy, the things look like separate things, sometimes a coincidence, and maybe understanding well the phi 12 could help in getting some more uniform knowledge about this, like getting various formulas. For example, taking all this together uniformly, or say all this so-called mirror moonshine also should have some uniform descriptions. It's very strange thing that I haven't told, but you can look for classification of Fano manifolds, of Fano triples. And then you have some particular genus zero modular forms appearing there, and there's some generating clouds. Probably Fano triples are kind of, again, their sections K3, mirrors is K3, and there should be some 512 understanding of all the modular forms appearing there.
It's in the group.
No, I see
from the point of view of geometry, it's completely strange that you get.
I see only one non-formal explanation for this effect. It was the idea of Eichler. He told us that we have 5 arithmetic operations. It's 4 usual arithmetic operations and the 5th operation modular 4. So it's the only very natural arithmetic operation which we can use in geometry and physics. So only one philosophical explanation.